All right, dudes and dudettes. Hope you're doing all right. Chapter 2, 2-4, solving equations with variables on both sides. After this lesson, I will be able to solve an equation with variables on both sides and identify equations that are identities, or some people would say have infinite solutions, and equations that have no solution. Here we go. Diagram gives information about the population of two towns. After how many years will the populations be equal? So if I look here, town A has a starting population of 3225, and they grow 100 people each year. Town B has a starting population of 3,300. They grow 75 people each year. All right, and I want to know when they're going to be the same. Well, this lady right here tells me if I make a table, it might help me. So, there you go, lady. So in year 0, or the starting amount, town A has 3225. Town B has 3,300. Okay, now each year, town A is going to gain 100. Town B is only going to gain 75. So in 1 year, they would have 3325, then 3425, then 3525, and you would see over here gaining 75 each time. At year 3, they have the same amount. So one way to solve this would be with a table. However, you can imagine that if it was, a large number of years was the answer, that might be, a little time consuming to just continue to make the table. So this section focuses on making equations and solving those equations. For this example, we could let y be the number of years and just set up a basic equation. So the starting amount plus the growth of 100 per year. The starting amount plus the growth of 75 per year. And I want to know in how many years is this population the same or equal to this population. So I just have to solve that little equation. So this is a equation that has variables on both sides. It's got y's on both sides. So my goal is to get all my variables on one side and all my numbers on the other. Use the same rules you've been using throughout the whole section. So I'm going to subtract 75 y's from both sides. All right, I can only take y's away from y's. Those are like terms, so I can only take variables from variables and numbers from numbers. So I would have 25 y's left, and now I'm just going to move all my numbers over to the other side. So subtract 3225 from both sides, and I wind up with 25y equals 75. Simple problem, divide it by 25, and y is 3. Obviously the same answer you got from the table, but really the section wants you to focus on solving equations. So in 3 years they will have the same population. Okay? So solve equations with variables on both sides. We use the same properties we've been using the whole time. We write a series of simpler equivalent equations. Get your variable on one side, get your numbers on the other, and then divide. So we got a bunch of examples here. Here we go. All right, so pretty basic problem. 5x plus 2, 2x plus 14. All right, I got to collect all the x's on one side and all the numbers on the other. Doesn't matter which side, as long as you get all your x's on one side and numbers on the other. I always try to move my x's first. You'll see why later on. Subtract 2x from both sides. So I went up with 3x plus 2 equals 14. The biggest thing is you can only subtract x's from x's. So if I'm taking 2 x's off of here, I have to take them off of the x's over here. I can't take them off the regular number. So 3x plus 2 equals 14. I got to get this 2 away from the 3 x's. So I'm going to subtract 2 from both sides. Whatever I do to one side, I have to do to the other. And now I wind up with 3x equals 12. Divide both sides by 3. And x is 4. So same process as the last couple sections. Just now we got some variables on both sides. All right, a couple more examples. Here we go. So 7k plus 2 equals 4k minus 10. All right, let's collect all our k's on the one side. So I'm going to subtract 4k's from both sides. That's going to get me 3k plus 2 equals 10. Subtract negative 10, sorry. Subtract 2 from both sides. 3k makes negative 12. Divide by the 3, and k is negative 4. All right, so no different than anything we've been doing. Here's another one. Okay, now here, when I first start, notice I have to do my distribution first because I got those parentheses in there, so I want to try to get rid of those. So I distribute the 2 That would get me 10x minus 2. Distribute the 3. That would get you 3x plus 33. Remember, he's got to go to both of those things. The 2's got to go to both. All right, and then from there, it's just like any other problem. Get your x's on one side, your numbers on the other. I'm going to chop a 3x off of both sides. That gets me 7x minus 2 is 33. I'm going to add 2 to both sides. 7x equals 35. Divide by the 7. And x is 5. Okay? Pretty straightforward. Number 4. More of the same. Same idea. Again, I got to do my distribution first because I got some parentheses in there with some numbers stuck in front of them. So I got to give the 4 away to both. So 4 times 2y and 4 times 1. And then I got to go 2 times y and 2 times 13. So I got an 8y plus 4 equals 2y minus 26. Get your y's all on one side. So I'm going to chop 2 y's off of both sides. Gets me 6y's plus 4 is negative 26. Subtract 4. And I got 6y is negative 30. Divide by the 6. And y is negative 5. Okay? Couple practical application problems. It takes a graphic designer 1.5 hours to make one page of a website. Using new software, the designer could complete the page in 1.25 hours, but it takes 8 hours to learn the software. How many web pages would the designer have to make in order to save time using the new software? Okay, so what do we know? We know that the current design time is 1.5 hours per page. We know that the new time, if I use this software, would be 1.25 hours per page, but it does take me 8 hours to learn the new software. So if I let P be the number of pages, so then my current software is 1.5 times the number of pages, so 1.5 times P, and my new software would be 1.25 times the number of pages, plus that initial 8 hours that I have to invest. So I want to know when they're the same, because anytime before that point, the old one would work better. Anytime after that point, the new one would work better. Okay, so if we look, and now it's just a variable equation with variables on both sides. Chop off the p's to get all your p's on one side. 0.25p equals 8. Divide both sides by 0.25. All right, be careful. 8 divided by 0.25 is going to get bigger than 8, and x is 32. So in 32 pages, all right, 32 pages, after 32, the new software would begin to save me some time. So I wrote, it takes the same amount of time, including learning the new software, for the designer to make 32 pages. So it doesn't matter if you used old one or new one, at 32 it's the same. Once the designer makes over 32, well then the new one works, saves me some time. Okay? Great. Another practical application, same idea. Office manager spent $650 on a new energy-saving copier that will reduce the monthly electric bill for the office from $112 to $88. In how many months will the copier pay for itself? Okay, well, the old machine is $112 per month. The new machine is $88 per month, but I had to buy the new machine, which was $650. So if I let M be the months, the old machine is 112 times the number of months. The new machine is $650 up front plus $88 per month. So when are they the same? Anytime after that break-even point, the new machine would be better. So it's an equation with variables on both sides. Chop your 88s off. I got 24m equals 650. Divide both sides by 24, and m is about 27.0833332. Okay? So the machine will pay for itself. The money saved in the electric bill will offset the purchase price in about 27 months. Great. There's two special cases. An equation that is true for every possible value of the variable is called an identity. Or we often say that that equation has infinite solutions. And then, for example, if you had like x plus 1 equals x plus 1, well, it doesn't matter what number you put in for x. The left side and the right side will always be the same. So another identity would be 1 is equal to 1 or 0 is equal to 0. All right. Equation that has no solution if there is no value of the variable that makes the equation true. For instance, x plus 1 equals x plus 2. There's no number you could put in for x so that the left and the right are the same. Or an equation like 1 is equal to 2. Well, 1 doesn't equal 2, and it never will. So that's a no solution kind of problem. Or 0 equals 1. Well, that's a no solution. Okay? So the bottom line is whenever you solve an equation and your variable is eliminated, the answer will either be infinite solution if you get a true statement out of it, 1 equals 1 or 0 equals 0, or no solution if you get a false statement, like 1 is equal to 2 or 0 is equal to 1. So let's look at a couple examples. So it's still just a regular equation. So here in the first one, I got to distribute because I have that 2 stuck to the parentheses. So when I distribute that 2, I'd wind up with a 10x plus 12. 10x plus 12. All right. And now for me, like I said earlier, I always move my x's first, just in case they were to be eliminated, like they will be in this case. So I subtracted 10x from both sides, and I would just get down to 12 equals 12. So my variable was eliminated. And right now I have a true statement. 12 is equal to 12. So this is a true statement. This would be an infinite solution problem or an identity. Some people call it an identity. You could keep going further, and if you chop 12 off of both sides, you would still get an identity, a 0 equals 0 true statement. So it doesn't matter whether you stop here or here, you're still going to get a true statement or a true statement, and therefore you should say that this is an infinite solution problem or an identity. Okay, here's another look at a problem like that. So there's nothing to distribute, but what I can do is combine my like terms on the right. So negative 3m plus 12m would make 9m on the right. Chop 9m off of both sides to try to collect your m's on one side, and you find out whether they're going to drop out. Well, as soon as they drop out, it's either got to be infinite solution or no solution. And if you look at what's left, negative 4 doesn't equal 5. So that's a false statement. So right now you would say that has no solution. Some people would continue and simplify it as far as they can, and you'd get down to 0 equals 9. Okay, well, 0 equals 9 is still a false statement, so that would be a no solution kind of problem. All right? Great. So basically, to recap, solving an equation. Distribute first to remove any grouping symbols like parentheses, and bust out any fractions if you have those. Okay. Number 2, combine the like terms on each side of the equation. Then use my addition and subtraction to get my letters on one side, my numbers on the other. Divide by whatever number's stuck to your variable, and then you can check it by plugging your solution back into the original problem. Does it make a true statement? Okay? Awesome. That's it for 2-4, my friends. I'll see you next time. Oh, and before we go, my dog's name is Lieutenant Columbo. If you write that on the top of your paper when you're done the 2.4 video sheet, show that to me. We'll give you a little bit of bonus. I'll see you next time. Peace.